to have the quiz 4 on Monday. So it will be our, revision tutorial of your module 4, and we'll be going for our some sort of problems that we are finding very often in the various tests, etc. We'll choose from there. Yeah, I have talked about the negative resistant devices. Okay. Now, question comes: if it is put in the circuit, what kind of volt ampere characteristic it is going to show? Let us start with a very simple circuit. This is my resistance. Here I am applying the signal. That is your DC V volt. Okay. This is my R. This I have taken from the book directly. There is a capacitor here, and there is a negative resistance device here. Now we want to model this one, voltage across this. Okay, this we want to model, or rather than you can say, I want to see voltage across this VC, and I want to find the current IC like that. Okay, that is of not much use. I can say I'll be going for this voltage V and the current through this, that is your I. So that means I'm interested in finding operating point of negative resistance device. And this operating point will put in the characteristic curve, that is your VI characteristic that is given to us by the manufacturer, or that we have seen by the experiment. That is the curve. We want to find there what is going to be the operating point. So what is the way I can write equation? There is a current I going from here, that I call it my IR. IR is the total current. It will be nothing but it will be your IC plus this current I that is flowing through the your negative resistance device. So operating point I want to find, V is here, R is applied here, V and R are there in my control. Okay, so set the operating point. So let us say I put it V and R, what is the operating point of that? Okay, so what is my IR? It is nothing but this V minus small v. Capital V, small v is this thing, this voltage. It is coming up to this point also. This is the voltage. This minor is voltage divided by R. This is going to be my circuit. So this is my equation number 1. And equation number 2 I can derive as your V, that is equal to your VC, or you can put here something like that. V equal to IR into R plus small v, like that. Okay, I want to find this I. How much is this I? So in terms of your This current IR is IC plus I. So I'll substitute for IR, IC plus I here. Okay?
Excuse me,
Yes.
sir, your screen is lagging.
My speech is not clear, you mean?
No, sir, screen is lagging.
Screen is lagging.
Yes, sir.
Lagging means what? Okay, I put it once again. You can see the screen now. Is the screen visible now? Fine.
Yes, sir.
Okay, it's fine. So here I want to find from a circuit, given a circuit, how to find operating point of NR, negative resistance device. In the circuit. Okay, that was the objective. And I have chosen initially a very simple circuit. Here is my voltage, DC voltage applied, V is applied. A resistance is put. In this circuit, there is a capacitor here. And there is negative resistance device here. This is my NR device connected like that. I want to find this voltage V and the current I. When I find this voltage V and the current I from some equation, okay, then I can find the operating point of this thing. Okay, so how to go about this? How to find this V and this I? Okay, to see the operating point of this thing. If capacitor is there, it will be charging exponentially like that. I can make it R and C combination such that it is charging with linear characteristic. That means charge is going as a linear. By making R very large, I can make it linear because see, R and C, I have to make it as large as possible. Tau should be large. If tau is large, e to the power minus t by tau will become small. And in that case, it will be approximated by minus t by tau. So it will be having a linear kind of effect over there. So that way we'll take that. Initially I'm coming as exponential one. So what is the equation I can write? One equation is this is my V, this is my IR. Then I want to find this I, there will be one current IC going through this. Okay? Fine. So my equation is IR equal to current through this, then current through the non-linear or negative resistance device like that. This is my equation number 1. Up to this point over there. Now equation number 2 will be what? V minus small v. Small v will be appearing here at any time t. V minus small v is coming here. Okay, so this will be given by IR into R. This is equation number 2. Now I have to write the equation in which this I and small v will be playing the role. Okay. Fine now? So now I can write here as, this was the place you mentioned that it was lagging. Now is it lagging here also? V I am writing as small v. Small v is nothing but voltage across the capacitor plus IR. IR is current across the capacitor plus this I. Okay? Fine now?
Yes.
Now? Okay, fine. So here I can write here, this is my VC. What is my IC? One by C, or you can say dV by dt. 1 by C will come here, isn't it? IC into R into C into this thing. So it will be your RC. RC dVC by dt is coming here. The VC plus this thing plus coming here as your IR. I into R. Okay? So this VC dVC by dt, here is your IR. And V minus VC is your IR into R. V minus VC I'm dropping that. Let me see something that I'm missing something. Where is that gone? Sorry, where is it gone? Yeah, this is the one I was talking. Can you see this? Okay. I said IR is IC plus I. Oh, I made me IC is C dV by dt plus I. That's what I made. And dV by dt from the second equation becomes V minus this thing. IR plus B. It's okay. Let me put this. RC dV by dt V minus IR plus B. IR plus V. Okay. Here. Here. Okay. So what we have got here is, I think I made some kind of confusion here. It is dV by dt, okay, will be equal to V minus
what is your problem? What is the topic you have chosen? Right?
this IR plus small v.
That is what your problem.
Okay. So RC dV by dt is the current passing through what? RC dV by dt
Because you have written this synopsis.
in the voltage.
3 years over, annual presentation, 2 years okay, annual presentation is there.
VC is the voltage across the capacitor. Okay. So operating point, how to find that operating point? I have to solve for I and solve for V. IR plus V. Solve for V is given. IR V is there. RC dV by dt is which voltage? It is charged to this. Okay, I think I got it. I'm just writing it here. I've used this new screen again, but here I'm putting this as a summary. I have got RC dV by dt equal to V minus some voltage V dash. Okay, RC dV by dt equal to V minus some voltage V dash. So when V becomes equal to this V dash, when this V becomes equal to this V dash, it will become 0. RC dV by dt will become 0. That means this voltage becomes constant. I'm coming to this new screen. Is it okay up to this point? V minus V dash, some V dash is coming there. There. Now I'm coming to the second screen. Sorry, I got lost in the meantime. I have got here RC dV by dt. Okay, is this voltage V minus some voltage V dash was coming. When V becomes equal to some voltage V dash. Okay, which we call as your, this is your equilibrium voltage VE. Okay, when V becomes equal to V dash, which is nothing but equilibrium voltage VE, then my dV by dt will become 0. And this will be the voltage, this will imply voltage at operating point. Voltage to get operating point. Okay, now similarly we'll go for the current now. What is this? The device characteristic is something like that. Okay, I have got V equal to VE. This is my V. Is voltage V. This is the characteristic here. So small v lying on this characteristic. So this is my V. I have to find what is going to be the corresponding I when V becomes my 0. When V becomes my 0, capital V becomes my 0, I am here now. That will be the current point at this point. When capital V becomes 0, how much current is flowing through that? In that circuit, if you remember, V minus IR was my V, this small v. Okay, so when V becomes your E minus IR into R, E minus IR into R was my V, small v. So from here, what is going to be the maximum current flowing through the device? When V becomes 0, maximum current will be flowing through the device. That will be there. Small v, I can write a current equation that is better. Here is my IR equal to IC plus I. So what is the maximum value here? We can calculate from here. IR is your IC plus I. When IC will be 0, I have to put IC equal to 0. So our dV by dt, this current I want to make 0. Then this will become your current I equal to your current IR. When capacitor current becomes 0, that means it is fully charged. It is fully charged with the voltage there. So IR becomes your capacitor is fully charged. So there is no current flowing through the capacitor. And at that time, I becomes your maximum. Will it be V by R or what? In the capacitor drawing all current. Okay. When the capacitor is drawing all current, I'm not able to get it. Capacitor draws all current. That means initially charge here is 0 across the capacitor. Charge is 0, so drawing all current. So I will E and I should become equal to your IR something. So this is my VE. I've given voltage VE here. Here current will be your, at that time how much current flowing through this? V has become equal to VE. No. This load line intersects here like that, and V equals equal to V dash equal to VE. Sorry, that was a mistake. Here is the current going curve like that. Here I have drawn the load line. This becomes my VE. And this becomes my IE. Yeah. Operating point. This is the voltage V I have applied. And this voltage and this current is for IR maximum. IR maximum. IR maximum is this. I drawn the load line. So this intersection point becomes your IE, this becomes your VE. That is the equilibrium point and this thing. So the supply voltage, if it is your VE, I am at the equilibrium point. But if supply voltage is not VE, is something V, then what is going to happen? That's what we are going to see. So IE and VE we can get. V is known to us. This is the V we have applied. What is the maximum value? IR maximum. IR maximum will be when the capacitor is short circuit. Okay. That means initially there is no charge on the capacitor. Okay. So IR will be equal to your I. So this IR will be equal to IE. IR will be equal to your negative resistance. That means V divided by Rn, negative resistance, is this value. Okay, so this current and this voltage draw the load line. This intersection is your VE, this will be your IE. I do it again. Confused or clear? Okay, now do it again. Okay, just wait. Yeah, I have written here V minus VE. That's I'm calling an equilibrium voltage. Okay, equal to RC dV by dt. So when VE and V equal to VE dV by dt becomes 0. Is the equilibrium point. Now coming to your this thing, current, your IR maximum will be equal to I passing through the negative resistance. Okay, that will be your V divided by negative resistance Rn. So your load line will be suppose I draw the load line here. This is your V, this is your V by Rn. But your intersection point is this thing. So this point becomes your VE and this point is your IE. So from the characteristic curve, you can find the operating point by finding the load line going through the. So it is cutting the S curve where this point or at other points also it is cutting from the load line you can find out. So you have to find what is going to be your VE, and this VE you have given as your in the previous page. Value of VE is your, once again, depending on the negative resistance, current actually, and your current flowing through the capacitor that way. No, not that. What was that? I into R. So negative resistance current IN R device into R plus this voltage across the negative resistance. This thing was your VE. That will become the operating point of this. And from the characteristic curve, you can find the load line. So curve has to be plotted first. Then you draw the load line, you got the operating point over there. Or you can do it by calculation also by deriving the equation. Okay. Now, I'll take some other example here. Suppose there are two negative resistance devices having characteristics like this. This is my I, this is my V. Negative resistance device is put in the circuit. Here is negative resistance device. Negative resistance device I'm putting as NRD. Okay? But DN is better for putting that. I'm putting here as a DN. And a similar device is put in series with this. What is the composite device now? And we are observing across this. This is my V and this is my I. Okay, so this is the put the two devices in series. What will be the characteristic of that? This way I have plotted. It is going like this. So what is going to happen? Here, none of them will be coming to this kind of your breakover condition until unless if this was your V1. Okay, if this was your V1, I goes like that. This was your I1. Normally we call as a peak, V peak and I peak. We call like that. Okay, corresponding to V peak, I'm calling it corresponding to the current is your IP, though it is not peak current like that. Here, where I have biased it, this one I call as I valley, and here also I call as corresponding voltage is one. So V I call as valley like that. So this is the condition. IV and VV is this, IP and VP is this thing. When the two are put in series, what is going to happen? Identical characteristics are there. Until this voltage becomes 2 into VP, this will not fire. And the reverse saturation current will be the same up to this point. When it has become 2 VP, that means VP appears here and VP appears here. So both of them will fire. Okay, and as a result, current will become something like that. Why only this current? Will the current increase at all? No, current is not, because same voltage V is applied to that, so current will not increase. So this will be my IV, IP rather, and goes like that. Here I am there. If I'm taking this itself as my IV and VV point, if I can take here also, doesn't matter. Okay. So here I can take anything. This becomes my IV and this will be my VV. So VV and IV will remain the same, but VP will become 2 VP. If I put them in series. If I put them in parallel, what is going to happen? This is, and this is I'm putting in parallel. Same device I'm putting in parallel. After that, they are added here. Going like that. Here what happens? Curve will be changed. Here it will be your VP only. Okay? Your IV, this is my VV, so VP, and IP will be from both the directions. So it will be something like that. So this is my VP. This will be your 2 IP. Because both the currents are added, it will break down like this. Okay. So here, this was my IV. It will become 2 IV now. What about this? This will be your VB only. So that's how this parallel and series connections of the negative resistor devices will be there. And accordingly, you can find what is the operating point by computing your VE and etc. First of all, you find your this supply voltage here. How much is your current flowing? Draw the line. Where it is cutting, that becomes a VE and this IE like that. So that is the operating point. You find it that way. I put the third example here, taking UJT for example. UJT, unijunction transistor. This is my unijunction transistor. This is emitter. This is base 1 or base 2. I am calling this as a diagram I discussed earlier. This is my base 1. So if I am applying voltage directly here, I have got the result I have shown to you. Now I am applying through a resistance. I am giving a power supply. This R. Okay. And I am observing the voltage here. This is my V, this is my I. This VI characteristic I am observing here. So what will be there? When this voltage was given here, let us say VB2, what was the voltage at this point? Okay. When VB2 was given, that is your VB2 divided by RB1 plus RB2. This was RB1 plus RB2. Okay. Into RB1. That was the voltage here. So VI characteristic we plotted. Okay. I have taken this one. This has to be above the cut-in voltage for this transistor. So that was the voltage. Now I am applying V here. How much VB2 will be coming? You compute. So that will be your V. That VB2 will be getting. If that is your cut-in voltage, you will be getting like that. And this one will be your VP. Related to your VP. So I think if you wait for, I'm coming after 2 minutes. So. Okay, I'm sorry. What I wanted to say that what was the voltage at this emitter when it fired earlier? Okay, it was V B2 divided by RB1 plus RB2 into RB1 plus cut-in voltage. When this voltage here was above this, it fired. Okay, now I am applying the voltage here, going through the R. I have to compute your VB2 here, that VB2 I substitute here. Now what will be the firing voltage? This voltage plus V gamma will be the firing voltage. So V gamma dash will be this voltage, okay, plus this thing. Plus VV2 into, I can put here as a eta. Okay, this plus this, if it is exceeding this, if it is exceeding this, here it will be exceeding this, only then it will be firing. And this one we can compute by taking this voltage V and this R and like that. So I'm writing the equation there. It will be over something like this voltage must be equal to this. I'm calling as V gamma dash. Gamma dash must be greater than equal to, or you can say not only that, sorry, I can say this, or V minus VB2 this voltage I want to compute. Okay, now it's coming from here. I think I'll do it tomorrow in the class. In a hurry, I'm not able to reach to that place. It will be something like that. This voltage V into 1 minus something like eta it's eta okay, I'll do internet, do it again tomorrow, because this VP has to be brought into consideration. So it will be over something exponential. If capacitor will come, capacitor is not coming here, so that is not required. So it will be over this. Equation written somewhere here. I cannot move this window. Anyway, I'll do it tomorrow. That is better. Your time is up now. I don't want to disturb them. Okay, it's better. I'll take it up tomorrow. Tomorrow we're meeting at 4:30. That will be the discussion hour, and then I'll be coming to. Okay then. See you all tomorrow again. Good day.
Thank you, sir.